So let's take a look. We've got test 3, big test, right? Big test coming up. So test 3 is on chapter 4, though. It's not on chapter 3, unfortunately. But it's pretty much all of chapter 4. Okay, 4:1 through 4:4. If you recall, 4:1 and 4:2 were primarily conceptual concepts, conceptual ideas. 4:3 and 4:4 were primarily mathematical based. Okay, so consider that when you're looking at your studying. There's going to be a decent amount of math problems because we've been doing a lot with math. Even the short answer, I might ask you some sort of mathematical relationship. I might say something like this. As the mass of an object increases, what happens to its weight? Show why. So you can show that, Fg equals mg, since m is directly related. If you have more mass, you have more weight. Or I might say, what happens to the amount of friction between the surface and an object if that object is heavier? Well, think about it. If you add more mass to something, you're increasing the weight. You increase the weight, you increase the normal force. More friction. So those could be mathematical / conceptual in the middle of the test. And then the beginning you'll have mainly conceptual with multiple choice again. Let's go through each of these 4 sections. What was the primary basis of the first section of 4:1? What was 4:1 all about?
Changes in motion.
Yeah, we talked about some sort of force causing some sort of motion, right? And we really alluded to inertia. We alluded to the idea of it. We didn't really get into it, I don't think, in 4:1. I think we waited until 4:2 to get into what inertia really is. But in 4:1, we really came up with the idea that as you apply some sort of a force, it's going to cause some sort of an acceleration. Okay, and we can think about this with and without friction, though. Okay, with friction, we can remember that it might not move initially. Go back to lab 4, the one that you guys turned in last week. I'm grading right now with the simulation. Sometimes you push on the file cabinet. It didn't always move. You didn't overcome what?
The love is terrible.
You didn't overcome what?
Well, initial friction force of friction.
Static friction force. Come on, get it right. Static friction force. It means something specific. It's not just the friction. Now, once you started moving the refrigerator, what did you then have to overcome continuously the whole time you were moving it? Now that it's moving, what do you have to overcome?
Kinetic friction.
Kinetic friction. Okay, now, a lot of you really struggle to answer some of those questions. For example, one of the problems said, turn friction off, apply force to an object, and notice what happens. And you saw that the velocity kept climbing because there was acceleration, and then release the force. When you release the force in the object, if there's no friction and it's moving, it will continue to move forever at a constant velocity. That's what inertia is. Inertia tells us that, if I'm moving, if I take this binder and I were to throw it across the room and it landed and there was no friction, it would slide forever. I apply force until it hits another object to cause it to stop. It's not going to stop. Okay, so a hockey puck on ice hits very lightly should technically make it across the whole ice rink if there were no friction. It should go on forever until it's like a wall, and a wall causes it to stop. So inertia tells us that unless acted upon by an outside force, friction is an outside force. Many people forget that. So unless an object is acted upon by the wall, by friction, by something else, if it's moving, it's going to continue moving. If it's at rest, this calculator is sitting still, unless I come by and smack the calculator or hit it or do something to it, it's not going to move. It maintains its state of motion. We talked about mass. I'm not talking a lot, by the way. I'm not writing a lot. So the things that aren't necessarily, things that you know already, maybe as I'm saying, you should probably jot them down, right? We talked about mass. What is mass? What is mass? This is conceptual stuff we're doing now. What's mass, Alondra?
How much matter an object takes up?
Yeah. How much stuff makes up an object? How much matter it's made up of? Now, we talked about the relationship between mass and inertia. Anybody remember that concept? What's the whole idea behind mass and inertia? How are they linked to one another? Kitty?
More mass means less inertia. Or no, more mass means more inertia.
Which one?
More mass means
Why?
because if something is heavier, then it's going to want to stay still.
Exactly. Think about it. Remember we did the example, I talked about a golf ball, a golf tee, whatever. Forget that. Think about this. Think about the incline plane ramp over there. If I were to walk up to that, well, if I were to walk up to Sierra's bag, or do whatever, kick her bag, it might move very lightly, right? If I kicked it harder, it would really move. If I tried to kick that, though, it probably wouldn't move very easily, right? There's a lot more mass there than there is here. The desire for that object to stay at rest is greater than Sierra's bag. Now, the same goes to thinking about objects in motion. Please think for a moment. You're at a stoplight. There's an 18-wheeler truck and there's a Corvette. The light turns green. The Corvette moves much quicker, much easier, right? Because there's a lot more inertia. It just wants to stay still. It takes a lot more force to get it to move. And you did that at the lab. I asked you to figure out what would the acceleration be, or the force be needed on a refrigerator to be the same as a textbook. And you recognized, I think, that it was like 20 times as much force was needed, because the mass was 20 times more. Well, the same occurs if an object is already in motion. So back to the 18-wheeler and the Corvette. Instead of being at a stoplight, the 18-wheeler, the truck, huge, big trucks carry all this stuff, and a Corvette are both traveling 70 miles an hour. Okay? They're on I-95 and the New Jersey Turnpike, and up ahead there's an accident. The Corvette barely has to apply the brakes and stops. Why does the truck driver have to really hit on those brakes to stop it? It's true. Why does he have to do it? The truck has so much more mass. The object's inertia is greater because it has more mass. Its desire to continue in that motion is greater. So you need to apply a greater braking force to the truck than you do to the Corvette to stop it. Because of its mass being greater, and thus its inertia or desire to continue in that motion being greater. Okay? That was like 4.1 and 4.2. Look at your notes for 4.1 and 4.2. See if you have any other questions real quick from those two sections. Take a quick look. You have them in your notability. See from 4.1 and 4.2 if there was something else that may have confused you along the way. I'll move on to 4.3, but I want to make sure that all those questions are answered first.
So
4.3 is where we start the math.
So from 4.1 and 4.2 it's all conceptual, right?
Yeah, it's pretty much all conceptual in 4.1 and 4.2. Anybody in here not get their quiz back, by the way, from the other day? This is all the other class, but I might have mixed one in. You all get this quiz back the other day? Okay.
Yeah.
And how about Lab 3? Did everybody get that one back in here?
Yeah.
The one with the projectile being launched at an angle?
Oh yeah.
I have yours, yep. So any questions? Look at your notes again from 4.1 and 4.2. Ask me some questions. Yes?
From 4.2, we did that one problem, like the crate being pulled to the right, like find the net force, or like, and that was.
We did a math problem from that section. You're right.
Yeah.
So that's a really good question. Look at 4.2, we did a math problem where we had to break it up into angles again, right? With cosine and sine. So this math problem in 4.2 is definitely fair game, but I'll probably end up giving you one like we just did because it encompasses that.
Okay.
So in 4.2, I said find the net resultant force and the angle which it acts. Well, to find the resultant force, you have to break the components and put it back together. I'm not going to ask you to do that directly, but I'm going to ask you to do the problems we just did where the forces are at an angle. So as a result, you have to figure out, breaking them up into components. Okay? Other questions on 4.1 and 4.2? All right, 4.3, we started with Newton's second law, which is where we began math parts. And this is what Newton's second law said. Okay? It also could have been written like this, and I'll put a biconditional statement to show that both could be written. It also could be written like this. And this kind of directly indicates that acceleration is directly proportional to the force, while indirectly proportional to the mass. Again, this is like your net force, don't forget. In case that's confusing to where we've been changing this word. The acceleration of an object is proportional to the net force applied. You push harder, it moves more or faster. Either one is fine. Okay? Again, you push harder, there's more acceleration. You push harder, there's more acceleration. But if you have more mass, what happens to the object? It doesn't go faster, it goes slower because it's heavier. Okay? So acceleration and mass are indirectly related the acceleration and net force are directly related, or applied force or net force, depending on the situation. Okay, again, another question that was in Lab 4 that some people really had trouble with. In Lab 4, I asked you to describe the relationship among F, M, and A. F and M here, right, the force and the mass, and the acceleration here. Okay, so know how to describe those. If I wanted to get an object moving with the same acceleration as another object that had twice the mass, I have to apply how much force? Twice the force. If I have, again, think about it, right? Logically. Here, you got one calculator. I won't mix them up. You got one calculator here. And suddenly, when you're pushing on it, you're moving with a certain acceleration. Suddenly you double the mass. Well, now you have to push twice as hard to get it to move the same way. Okay? So more mass means you have to push with more force, proportionally speaking, to keep up with the same acceleration. In your lab, the file cabinet was 20 times the mass of the textbook, so you had to apply 20 times the force on the file cabinet than you did on the textbook to get the same result of acceleration. Some of the forces that we talked about. Weight. Oops. The weight of an object is given as Fg. That is equal to mg. Why do I feel like weight is spelled wrong?
Yeah, I just
Always.
Isn't I before E?
Always feel like that.
No, you're right.
It's right.
right.
It's I before E, except after C,
And wait.
or sounded like nay as in neighbor and way, right? That's what they say or something like that? It always looks wrong. So Fg,
It's weight,
I know, but yeah, height, what is height? Is height H-I-E or H-E? My spelling is terrible.
So she said it sounded the same.
No, she was saying, no, it's
Okay,
spelled,
height,
it's spelled the same way, but it's.
There,
I don't know. So the idea behind weight is that weight is a function of two things: an object's and the planet's. Yeah, right? They're both right. You question both. The weight is a function of the object's mass and the gravitational field on that planet. So if I tell you in a multiple choice that an object travels from Earth to Mars, which of the following factors changes? The mass doesn't change. The mass is the mass. But what changes? The weight, because the gravitational field is now different. Okay? If I tell you that an object loses mass, half of the object drops off. A rocket takes off and burns a bunch of fuel, and as a result, the mass of the object is now less. Well, if you have less mass, you also have less weight. Just like on the moon, if you have less gravity, you have less weight. If the moon's gravity is a sixth of the Earth, your weight is a sixth of that on the Earth. If the gravity on Saturn is 4 times that of Earth, it's not, it's 4 times that of Earth, your weight on Saturn is 4 times that of Earth. They are directly related. Okay? Frankie, go ahead.
No, you just, I was just about to ask, are you going to do one of those,
Relationship kind of things?
planet ones?
Yeah, definitely expect stuff like that. Definitely expect that. Multiple choice or short answer, either one. Not mathematical or something like that. Mathematical problems will all take place on Earth. The last part, because I want you to understand that G is definitely 9.81, just so we don't have confusion there. I'd rather see you get the work done than test you on a different planet
Wait,
there.
so you're not going to do one, because it's on the problem sets. There's one where...
So like if I say to you in a part 2, not part 3 mathematical, the part 2 where it's like the short answer, I might say to you, an object's mass triples. What happens to its weight? Well, it should triple. Or I could say to you, an object travels from this planet to another. If the weight on Earth is 30, but the gravitational field on the other planet is a third of Earth, well, a third of 30 is 10. So you can find out the weight very quickly. You don't need to really do math for that. It's more of like just conceptual stuff with very minimal math. That would be like a part 2. Part 3 will all be on Earth. Okay? What other thing do we have? We have the normal force. What is the normal force? Who could describe what that is? Remind us, what is the normal force? How would you put it in your own words? Normal force is what kind of a force? What does it do? How does it act? Nobody, really? Just give me your own words. We've talked about normal force so much. You have to be able to describe this in your own words.
Well, it's just what it is, the surface.
From the surface, good.
It's like perpendicular.
Very good. That's exactly right. It pushes up from the surface perpendicular. You could also say that it's a reaction force. It's a reaction. It's a reaction to the object's weight. Okay, it pushes up from the surface, and it's always perpendicular from the surface. Okay, it's a reaction to the weight. The normal force really is a result of Newton's third law. Newton's third law says for every action is an equal and opposite reaction. Well, right now, this calculator is pushing down the table. For it not to move and be in equilibrium, the table's got to push back up. The table's got to push back up with a normal force. Normal means perpendicular. That's where the name is derived. Okay, it means perpendicular to the surface in all directions. The other force that was very important was the frictional force. Let's talk about that for a little while. There's a lot we could talk about for friction. Friction is exciting. There's two types of friction. What's the first type of friction when an object isn't moving? When it isn't moving.
Static.
Static friction. Static means unchanging. In kinematics or in engineering, you also use dynamic for change, and we're going to use kinetic though instead. Okay, we've got static, kinetic. Who can tell me something they know about static and kinetic friction? Maybe with respect to one another. With respect to one another. Yeah.
Static friction is greater than the kinetic friction.
Yeah. It takes more force to get it moving, meaning static force of friction is greater than the force it takes to keep it moving, the kinetic force of friction. So let's jot that down real quick. How would I write that? I would use an inequality maybe, right? An inequality is a comparative statement. Remember inequalities from math, so I might say that the force of friction due to some static force is always greater than or equal to the force of friction to kinetic. It could technically be equal. Some materials are very close to equal, so they have to say greater than or equal to. Okay, but the static force will never be less than the kinetic force. Well, if that's true, I could technically do this. Right? Isn't that what the formula is? Can I just plug in? For FF, I can plug in UFN. For FF, I can plug in UFN. I'm putting S for static and K for kinetic. But Fn is the same on both sides. So what conclusion can I also draw? I could say this. Cross these off. And that second conclusion is also true. The mu value for static between two surfaces is going to be greater than or equal to the mu value for kinetic between those surfaces. These two statements are really saying the same thing. One is talking about the force of friction being greater static. One is talking about the kinetic of the coefficient of static friction being greater than the coefficient of kinetic. This is for a given set of surfaces. So again, I'm talking about my hand on the desk. It takes more force to get it moving, but once it gets it moving, it doesn't take as much force to keep it moving on the desk. For two given surfaces. If I'm looking at metal and ice, and then in another instance I'm looking at wood and concrete, those mu's are totally independent, mutually exclusive mu's. You can't relate the two of them at all. I might say to you though, which of the four has the lowest mu value? From your lab, you should know as a result that, for example, Teflon was the lowest mu value in the lab by far. Felt was the highest in the lab, cork was the middle. I'm not going to ask you to memorize them all, but you should know, for example, that Teflon is definitely one of the lowest things, or metal on ice would be what kind of a mu value? Metal on ice. Think about ice skates, they're made of metal, and ice is ice, ice skate on ice. So metal on ice, what kind of a mu value? Yeah, really, really low mu value for metal on ice. What would be something with a higher mu value? Something where you want a lot of friction. What would you want a lot of friction between?
They have the socks with the sticky things on them.
Perfect. The socks with those little sticky things have a higher mu than just regular socks. Absolutely. Absolutely. Why do you think little kids have those, by the way?
That's the
Yeah. They don't just wear, they don't not put babies with baby socks. They have little grippers on the bottom and they're like the onesies they wear.
I was just thinking
It's like a little plastic lining. It's so they don't slip, really. You're increasing the mu value. That's what you're doing. Okay? In another chapter from now, we're going to look at the work kinetic energy theorem, which relates friction to work. And I'm gonna have you guys an extra credit where you're able to slide around your socks and measure stuff. It's kind of a cool extra credit. It's from the movie,
Tom Cruise.
yeah, but what's the movie with Tom Cruise? It is Tom Cruise, Risky Business. Remember? He comes in and he's like boxers, he's like playing guitar. He like slides in on like his socks. Risky Business. So, another Tom Cruise thing. Funny, he comes up a lot. Anyway, friction, you get the idea? Yeah.
When is our extra credit due?
For the elevator one?
Yeah.
I always do it before like the test it's on, so tomorrow would be great, maybe by Wednesday at the latest. Okay, before you guys leave for junior retreat would be good, because I'm going to have grades done by the weekend, so I'm not going to include it if you don't get it before you leave. That's a lot of people in trouble with getting an analog scale. I know. As long as your digital scale is able to vary weight and it shows the change in weight as you're moving, as long as it doesn't lock into a weight and like stay on it.
That's
You
what
know what
I
I
did.
mean?
Do you know what I did?
I saw yours. It was good. You got on it right as it started to move, right?
No, I did it, and then I broke the rules, and I got on a freight elevator, and I started moving it by myself. I got in big trouble for this with my building, but I was moving it, and the thing was very, very good.
I saw your video already, yeah. It was you that submitted it like a week ago, right? Yeah.
I got in a lot of trouble for my building.
What else? Let's see. So, think about this. Friction is directly related to mu. More friction. Makes sense, right? It's also directly related to Fn, which tells us, since Fn is related to Fg, right? The heavier the weight is, heavier pushing down, the more Fn you have. So the heavier the weight, the more Fn, the more Fn, the more friction. That's the transitive property. Think back to math. More weight is more Fn, but more Fn is more Ff. So in the end, more weight is really more Ff. So if you have a heavier object, there is more friction between the object and the surface. That's why it's harder to push a heavier object. Think about you pushing a couch, and then your annoying little brother or sister jumps on the couch while you're moving it. Doesn't it slow down? Of course it does, because now you have more friction between the couch and the floor. So you increase your weight, causes an increase in Fn, which causes an increase in Ff. Okay, so the weight of an object is also directly related to the force of friction, but it's not obvious. It's not obvious because it's not in the equation here. You see what I'm saying? Okay, the more weight an object has, the more friction it will have between the object and the surface. What else? I want to do maybe a mathematical. I could do an example of, again, we just did one, but I'll do another. I'm trying to think conceptual of anything else. Yeah.
Could we do a mathematical example where there's a problem with static friction? We're trying
Sure.
to view S.
Yeah, let's do that. Let's do one of those. It takes 560 newtons or 650 newtons just to get an object moving, but it only takes 560 to keep it moving at a constant velocity. And you have to find us and uk. So let's do a problem first. We have to find us. Then we'll talk about uk. So let's say you want to write these down. You can write these words down. I'll dictate. It takes 310 newtons. It takes 310 newtons for an object to begin to move. For an object to begin to move. If the force is applied, God bless you. If the force is applied at an angle of 12 degrees, God bless you, above the horizontal, if the force is applied at an angle of 12 degrees above the horizontal, and the mass of the object, I'm hoping these numbers work out. We'll do it and we'll see how it works. And the mass of the object is 15 kilograms. Then determine, and the mass of the object is 15 kilograms. Then determine the coefficient of static friction. Then determine the coefficient of static friction. Remember, I said it takes this much force to get it moving. I'm not talking about while it's already moving, while it's in motion. So I'm specifically talking about static friction. The instant before it begins to move, it needs whatever force I told you, 300?
310.
310 newtons. Okay, so if I'm drawing a free body diagram for this, First of all, the force is at an angle of 12 degrees. Is that correct? 12 degrees?
Yeah.
The force applied is 310 newtons. Okay, so if you want to completely forget like writing FP, you can just write the number if you want also. Right? We'll do this all with math. We'll do it without variables here. We'll plug all the numbers in to make it a little easier if it helps. The weight of the object. What's the mass? What did I tell you the mass was?
15 kilograms.
And it's always mass times gravity. That's the weight of the object. I'm not even putting my labels of forces down. I can. Okay, I could call this FP and call that theta and call that FG. That's what they are. So if you want to, go ahead and write them. Okay, if you've been used to that and you're accustomed to it and you think it's easier to have these labels here, you could use just the labels instead of the numbers. Whatever you think is easier. What opposes the motion of this object? What always opposes the motion of an object?
Normal force.
Normal force opposes the motion down. Very good.
Yeah,
And what opposes the horizontal motion?
friction.
Friction. Now, we are looking at this problem the instant before it begins to move. Write that down if that's not clear to you by now. Whenever you're finding the static coefficient of friction or the static force of friction, it's the instant before it begins to move. Remember, the force of friction takes on a range of values. I push the desk with 1 newton. It doesn't move, so what's friction? For it not to move, I push with 1 newton, what does friction have to be? 1 newton. I push with 2 newtons, it doesn't move, what's friction?
2 newtons.
But if I push with 3 newtons, friction can't be 5 newtons, right? It can't be more than the amount I push with. So friction is always a function of how much I push with, until what happens? Until I get it to start.
Surpass its friction.
Yeah, and that's what I'm telling you. 310 is the amount that is needed just to get it to move, but at that angle. At that angle. Okay? So it's not really moving. It's the instant before it begins to move. So write this down, please. Mass was 15, right? Okay, everything else is on the diagram given. All our numbers are in the diagram. I don't need any more givens anywhere. FFS. I could write that equals mu Fn if I want to. Mu S Fn. There's my equation for that. I could write it right in the diagram if it helps me. Whatever helps you, okay? The idea, though, is the same still. Look at the x and look at the y. In the x direction, what do I have to do with Fp? Fp is acting at an angle, so how do I get the x direction for it?
Oh, you do, what's the sign? Cosine.
So you do, I was gonna do 310 cosine 12.
Good, Frankie. Okay? Fpx is 310 cosine 12. What's Fpy? Instead of cosine, simply sine. In yellow, I have my new vectors, so you know what I'm going to do? Because I already have my new vectors in yellow, I'm going to get rid of all this junk because I don't need it anymore. I've kind of replaced it with what I'm writing in yellow now. Okay, so replace the one vector at an angle with its horizontal and vertical components respectively. And now F equals ma is very easy because everything is in some perpendicular direction. In the x direction, I've got 2 forces in this problem. 2 forces in the x direction. What are they? In the x direction, net. Okay, so FPX and FFS. Very good. So negative plus, how would you say the next one? And how would you say FPX? Equals MA sub X. What is A sub X though? What's the acceleration in this problem? 0. Okay, we're looking at the instant before it begins to move. We're trying to find out what mu is, so we can go ahead and plug in. We could say, all right, well, this is just mu s. It's an ugly s. Let me fix that. times Fn plus Fpx. We have a number for that. 310 cos 12 equals 0. That's all I can do in the x direction right now. Why do I know I have to stop right now in the x direction? What's the indicating factor? What's the thing that notifies me I can't go any further in the x direction, Ellie?
You don't know.
You don't know Fn. To know mu, you need Fn. So let's figure out what Fn is by looking at the y direction. In the y direction, we definitely have Fn. It is indeed. All right, so in the y direction, Fnx up, Fgx down, and Fpyx up. Okay, I'm going to put 0. It's really may, I should put. That goes to 0. Ay is also 0. Okay, I'm not going to ask you a problem. I'm going to tell you right now. I'll tell you right now that it involves vertical acceleration. So you could assume for this chapter that ay is going to be 0 for these problems. Okay? It's not going to have vertical motion to it also. That'd be really a much more difficult problem. And we just don't have the time to take a lot of time to go into that right now. All right, so, oh, come on, move diagram. So we want to take a look in the y direction. Fn is what we're looking for. Fg is mass times gravity. That's given right here. It's in our free body diagram. We drew it earlier. Fpy we wrote down as 310 sine 12 degrees. So as a result, you could solve for Fn by adding 15 times 9.81 to the right, subtracting 310 sine 12 to the right, get Fn in the y direction, plug Fn in the x direction, and solve for mu s. Solve for mu s. Now, pause for a second. I know you want to do it. Pause, because what time is this period going to end at? Oh, okay, solve. And then we'll go. Yeah, go to bed. I don't know we have that much time still. Go ahead and solve, and then I'll make some conclusions at the end then. What was that?
I got 211.6. I got 82.3. Yes.
You got 80 what?
2.3.
Yes,
You-
I got
Are you in, you might,
it. That's 82.7.
are you in radio mode or something? Check.
Check your mouth. Compare your degree.
So take a look at your work. Nat, compare yours with hers. 80 what?
No, do it separately. Do like 15 times 9.
Those need to be in like their own parentheses if you want.
You have to put these over here. No, you have to put these over here, so it's like
Oh,
positive.
okay.
Yeah, you added it.
What was the number again? 80,
82.3.
I got 82.7.
Yeah, me too. 82.7.
7?
Yeah.
Check, Nat.
Oh, 82.65, my bad.
That's the normal force, right? That's how much the floor is pushing back up with, 82 newtons of force. It's not equal to the weight. Remember, the weight is right here. Here's the weight, 15 times 9.81. But because this person is kind of pulling up, it's helping the normal force out. So the weight of this one would be like 100 and, what, 47.5? 147.5 or something like that. So the weight is actually 147, but the normal force is only 82 because you're helping by pulling upward a little bit. That's why the normal force is a little bit less. These are multiple choice questions that I will ask, right? Okay, it's less than the weight because you're pulling up a little bit to help out the normal force. Take that normal force, plug it in now. Plug it in right up here. Take the normal force, plug it into the x direction, solve for mu s. Remember, there's a negative sign in front of it, so you're going to obviously move the 310 cos 12 over by subtracting it, and then you should divide by negative Fn to get rid of the negative.
positive.
Yeah, you got a positive answer for sure. It's a negative over a negative.
To do negative.
Oh, yeah, you used over.
Move the 310 cos 12 over. I'll write the answer at the bottom. Okay, I'm going to move this 310 right here. 310 cos 12. I'm going to move it over to the right-hand side. Then I'm going to divide by not just Fn, but negative Fn. Divided by 82.7. And that's a negative number there, okay? I wrote down negative 82.7 there. Negatives have to cancel. You'll never have a negative mu. You will absolutely 100% never have a negative mu. If you do, you did something wrong. What do we got here?
I got 3.7.
3.7? Did others get that?
Well, 3.6.
It's a very, very, very high mu value. That's like something that is crazy high friction. Usually don't get mu values greater than like 1, 1.5. Why is it a very large number? Because I just picked random numbers for this problem, okay? Don't let that confuse you by any means. Traditionally though, mu will range between 0 and 1 for the most part. You can have things that are higher than 1, which is a little bit odd to see, but it just means they have very, very, very high amount of friction between the surfaces. Now, how would this problem change if you was like the problem set, and I now said to you, it takes not 310 newtons of force, but only 300 newtons of force to keep it in motion. Right? If I said it takes not 310 newtons of force, but simply 300 newtons of force to keep it in motion at a constant velocity, or something like that.
Acceleration will be 0.
Acceleration could or could not be 0, good, depending on what it is. And what would you be solving for? Would you still be looking for us? What would you be solving for then? Mu k. So all you have to do is the same problem. That's why I solved generically, by the way. See how we have all these numbers in here? If I had solved generically, like look at Fn. Isn't Fn, look at Fn, isn't there 310 here?
Yeah.
See where I'm pointing? So the problem is that if I change up this and I say it only takes 300 newtons, this has to then change to 300, which changes this answer. This has to change to 300, so this answer has a different number here and a different number here. So when I leave everything in variables, it allows me to make a quick change. And I don't have to actually do anything mathematically much different. Okay? Recognize that if it's in motion, if it's in constant velocity, acceleration is 0, or you have to find the acceleration depending on the problem. Okay, practice the next week. Practice. I think that's it for time. We have like a minute. Any other questions you might have? Anything you're thinking right now?
So would you say that the multiple choice and short answers will be mostly theoretical, and then
The multiple choice will be mostly theoretical, if not all theoretical. The short answer might have like a little bit of like simple math involved in it, like I've had before.
so would you suggest not going over obviously the whole thing, but trying to go with the math?
I would focus on the math because when you do the math, usually you learn the conceptual stuff also. You know? I mean, you should definitely know your concepts, but we also went over them this period. Guys, a really good resource. Some of you have been struggling greatly on multiple choice. I've been waiting for people to like just pick this up. You can look at like old New York State Regents exams, old SAT subject physics tests that are published online, multiple choice questions on courses. Look at those for sample problems, okay, for multiple choice, if it helps you. Don't forget to tell me if you have extended time. Email me tonight, please. Let me know what period.
Wait, still recording.
I can stop recording. Thanks. Perfect.